Okay, so a little bit more Chapter 15 that we're going to talk about. We're actually kind of done with the actual material of Chapter 15. I just kind of want to, bring it all together a little bit and show you some examples of, talk about how all these different ideas can be used in practice, when it comes to where does the rubber meet the road, how do you actually compute stuff, right? Okay, so, I have, this thing I call a strategic summary, for how to compute line and surface integrals, and it's just a strategy that you can take that will hopefully lead you to the most efficient way of solving the problem. But there's a certain amount of judgment that's involved along the way. Okay, so step one: make sure to understand the question. What kind of integral are you looking at, and where does it fit in on which diagram? So, as y'all recall, I'm a big believer in these diagrams. I think these are really useful. There's the R3 diagram. There's the R2 diagram. It wouldn't quite all fit onto the screen. There's also this bit at the bottom. Those are the lifetime theory. Everything has a lifetime of 2, those theorems. But most of what we're going to be looking at here are these. So for a given problem, just identify where you are in the diagram. So if you've been asked to compute a flux integral, okay, that's what you're trying to compute. Go ahead and just, think in the context of the diagram, where are you? Okay. If you're looking at a line integral, then you're here. Unless the line integral is in 2 dimensions. If the line integral is in 2 dimensions, well, then you're not in the R3 diagram, you're in the R2 diagram. So just make sure to figure out where you are. Okay, that said, once you know where you are, there should be 2 boundary theorems that are candidates, may apply to helping you to compute the answer you're looking for. So, for example, if you're looking at a line integral in R2, well, here's your 2 candidates. Right? You might be able to use the fundamental theorem of line integrals. You might be able to use Green's theorem. Maybe, maybe not in both cases. But those are the candidates. Let's not talk about the divergence theorem. Right? Likewise, in 3 dimensions, if you have been asked to compute a flux, here are your 2 candidate theorems, Stokes' theorem, Gauss' divergence theorem. It wouldn't make any sense to try to figure out how you might be able to use the fundamental theorem of line integrals here. It just doesn't connect. It's not related. It's got nothing to do with this question. And so likewise, don't take the vector field that you've been given. Don't try to take the anti-gradient of it. It doesn't. Why would you take the anti-gradient of this? It doesn't matter. It's got nothing to do with what you're actually trying to compute, right? So again, the diagram will kind of tell you what it is that you might reasonably be interested in. So good thing to capitalize on. Okay. All right. I think it's nice to, I'll say, compute the appropriate operator. And try to decide which boundary theorems might apply, and that'll be part of it. So, for example, if you are looking at a line integral in R3, well, that vector field that you've been given, compute its curl. Because the diagram says so. You might think of in those terms if you like. So now, why would we compute the curl? Well, there's actually 2 ways that this might help you. On the one hand, it's possible that you might be working out this line integral using Stokes' theorem. And if this is the case, if you do end up using Stokes' theorem, notice you need that curl. It's part of your answer. Okay. On the other hand, it's entirely possible that you will instead be using the fundamental theorem of line integrals. And how can you decide if you even can use the fundamental theorem of line integrals? Well, you need to know if there is an anti-gradient. And a good way to decide if there is an anti-gradient is to compute the curl. Right? So one way or the other, curl gives you interesting information that may be relevant, likely to be relevant in your calculation. Okay. Okay, likewise, if you're looking at a flux, whatever the vector field is, whose flux you're interested in, compute its divergence. See what you get. It's liable to be interesting. Might not, but it's a good thing to look at. Let me warn you, though, about one thing, and that is that if you've been asked to compute a line integral if you were to take that vector field and compute its divergence, it doesn't look good, right? So please don't, right? Don't compute the divergence. Don't think in terms of, I'm going to compute everything in sight. Something I compute might be relevant, right? Because we're aware of that strategy. And the point is, that's a giveaway that you don't know what you should be doing and you don't know what the right ideas are for a problem like that, right? So don't compute the divergence just cause. Right? Keep in mind, so here's related. In some contexts, in some high school contexts, teachers make a decision that, wrong answers won't count against you. When that leads to this ridiculous strategy of write down everything that might possibly be relevant, because after all, it couldn't hurt. Right? But we don't do that. It doesn't make any sense, really. Well, of course, what we're doing in this context is we're grading you based on what's written down. What does it look like you really actually understand? Right? And if you write down things that don't make any sense, it makes it look like you don't understand. Right? So, anyway, keep in mind this is an adjustment, this is a transition that has to be made sometimes for some students from the high school setting. So think carefully about what you should compute and compute that. And don't compute something that doesn't make any sense. Okay. Alrighty. Don't forget also, path independence is always on the table. Surface independence, likewise, right? I'm not saying you should use those if they apply, but I'm saying it's worth noticing whether they're even an option, because they might be good choices, right? Likewise, always have your eyes open, head on a swivel, right, for the possibility that maybe in your calculation a certain dot product that you're doing is constantly zero. The vector field is constantly parallel to the surface, and therefore perpendicular to the normal vector, and therefore that dot product is zero, and therefore the flux is zero, right? So always be on the lookout for that kind of thing. Geometric coincidences, I call them sometimes. And so having done this, having gone through and identified your candidate boundary theorems, consider the possibility that maybe path or surface independence, considering the possibility of possible geometric good fortune, you're going to have various ways that you could conceivably answer the question. And then here's where the judgment comes in. Try to eyeball on the question and ask yourself, how hard is each one of these approaches going to be? And do whichever one looks like it's going to be the most reasonable. So anyways, like I say, a certain amount of judgment there. Okay, so here's some examples. Got a vector field, got a curve parameterized for us. Right? We're being asked to compute this line integral. The phrasing, the presentation of the question almost kind of suggests that you should do the pullback. Right? Plug and chug. Right? dx is x prime dt and all that. Is that the best approach to solving this question? Well, like I say, let's consider our options. So first of all, where are we on which diagram? We're looking at a line integral. Now, are we in the R2 or R3? Well, our vector field has 3 coordinates. Analogously, our parameterization has 3 coordinates. We're in R3. Right, so we're looking at a line integral in R3, and so we're computing one of these. Here's our 2 candidate theorems. We're going to steer very clear of divergence and triple integrals. Right? Don't do any of that. If you see a triple integral on the page while you're trying to compute a line integral, that looks really bad. Right? So keep that in mind. Okay, so we're going to look for these 2 possibilities. Now notice that the diagram is pretty much telling us that this vector field, I should compute the curl of it. So let's do it. Let's compute the curl. Coming back over here. The curl of this, where am I going to write this? The curl is, well, there's that whole formula you've got to do. My little personal shortcut mental trick for doing this is to recall that curl is a symbolically anyway, a cross product. Cross products are computed with determinants, and so I actually will write on here, in my mind at least, partial with respect to x, partial with respect to y, partial with respect to z, and then E1, E2, E3. And so this little matrix that I've made up here, this little 3x3 matrix, that's what I'm thinking of when I'm computing the curl of this thing. You can memorize the formula if you want, but I warn you, if you memorize, wrote the formula for curl, then at some point, maybe not for the third midterm exam, maybe not for the final exam, but eventually you're going to get something backwards at some point. It's easy to make that mistake. So I like to do it this way. Anyway, that said, you don't have to write that down. In fact, I never actually write it down. I'm just thinking of that in my mind. And so, with that in my mind, I'm thinking to myself, okay, well, the first coordinate, I'm going to be taking the y partial. Let me switch back to the highlighter. I'll be taking the y partial of that and then subtracting the z partial of that. And, well, that y partial is 1. That z partial, 1. So I have 1 minus 1, otherwise known as 0, which is nice. Okay, the second term, I'm going to have the z partial of that, 2x, minus the x partial of that, also 2x. So I have 2x minus 2x, also 0. How nice. Things are looking good. And then lastly, I have the x partial of that, which is 2y, minus the y partial of that, which is also 2y. And so, big win. The curl is indeed 0. All right, so going back to the diagram, we computed the curl. We got 0. And that means that there is an anti-gradient. Therefore, I can use the fundamental theorem of line integrals. And that's a reasonable candidate for how to solve the problem. How are we doing? Quick pause before we go on to the next thing. Okay. All right. Now, before we jump in and start, moving, let's consider the possibility that, hey, maybe Stokes' curl theorem might apply. Maybe, who knows, that might be easier than using the fundamental theorem. Seems unlikely, but let's just explore that possibility. How would Stokes' curl theorem apply? I would need for my curve, I would need for that to be the boundary of a surface. You have to have a surface to use the theorem. You have to have let me say that better. They have to have a surface for the theorem to even make any sense at all. Right. Okay, so let's look at our curve. Is this curve a boundary of something? And wow, I mean, that's a little hard to tell at a glance, but I'll make the observation. Curves that are boundaries have to close up. They have to start and end at the same point. If a curve doesn't start and end at the same point, it's just not a boundary of something, right? So this one is, that one is not. So it's a pretty easy test. Now, there is a kind of rare counterexample to this argument. You can have what we call a knot. Right? So this starts and ends at the same point, but inside of R3 at least, it's not a boundary of anything. So, right, so little weird counterexamples like this. Turns out this is not something you need to worry about. If you were to ignore this completely, it's not a problem. Okay. As far as Math 212 is concerned. So, let's just look and see, does this curve start and end at the same point? Well, plug in t equals 0, and you get x of 0. Let's see here. T equals, I get 0, 1, 1. Right, now, what is the ending point? The ending point, well, we'll take the last value of t. We'll plug that in, and we get x of 1 is, well, let's see here. Negative 1, comma. At this point, I don't really care. Right? Clearly, no matter what these remaining coordinates are, clearly these do not start and end at the same point. These are clearly different points. Right? So this is not a closed curve. So this curve is not the boundary of anything. It's an open curve. It's not a boundary. If it's not a boundary, then you could not possibly use Stokes' curl theorem. Doesn't make any sense at all. Everybody follow my reasoning there? Okay. All right. Okay, so here's our candidate, and you can. I mean, you can at a glance. Do any geometric coincidences jump out at you? No. It doesn't look likely either, and I feel like it would not be a good investment of my time as a student taking an exam to look for the possibility. And nothing's leaping off the page as likely, always perpendicular. It just doesn't look like one of those. Right? So probably no geometric coincidences. By the way, path independence is an option, right? We know curl is 0. So I could conceivably use path independence. I could take this path and replace it with another easier path. But as we discussed when we were talking about path independence, but anytime you could use path independence, you could also just use the fundamental theorem. And the anti-gradient's going to be nice and easy here, right? Easy anti-gradient. So what I'm going to suggest that you do on this question is rewrite this as integral of some sort of a gradient. Identify what that is, and your answer is f of b minus f of a. And I'm going to let you all work out the details on that. This is more of a diagnosis, strategizing discussion than the details. You all know how to do those details. Yeah? Everybody happy? Okay. All right. Next example. You will notice that this looks kind of like the last curve. It's just a little different. Tweak things around just a little bit. It's a totally different vector field. But it remains that we're looking at a line integral in R3. So we're still, back to our diagram, we're still looking at one of these. We still have these two candidate theorems. We're still going to compute the curl as the diagram directs us to do. We're wondering what that curl is so we can decide, what might be my eventual integrand, or does my anti-gradient exist. Okay. Excuse me. So let's get to it. Let's compute this curl. By the way, can anybody compute this curl at a glance? There's a real quick way to compute the curl here. I'll show you. It's a neat trick. And that is to realize, well, look, you're going to be taking a bunch of partial derivatives, but all of the partial derivatives that you're going to be computing are sort of, I'm going to call them diagonal-ish, right? And notice, this first coordinate only has x's in it. That means that its y partial is 0 and its z partial is 0. And that's obvious at a glance. There's only x's in that formula. Likewise, there's only y's in here. So that means that its two partials that we're going to be taking when we're computing curl. Obviously 0. And this one, its two partials, by virtue of having no x's and no y's. Obviously 0. So that's a real neat little trick to be on the lookout for if your vector field is only x's, only y's, only z's. Curl is 0. Yeah, nice little bit of good fortune there. Good news, curl is 0. Going back to our diagram, this is 0. Therefore, there is an anti-gradient. And therefore, you can use the fundamental theorem of line integrals. Yeah, everybody happy? Okay. Alrighty. By the way, notice if you were to do this, if you were to say, well, look, I love the fundamental theorem of line integrals. It's easy to use. So if I ever encounter that the fundamental theorem of line integrals is on the table, I don't need to know my other options. I'm just going to plow forward. I want to point out that if you do that, if you do just plow forward with this, you start to realize that there's a potential for this to actually get pretty ugly. Because you're going to have to take some antiderivatives. You're going to have to take an anti-partial of that with respect to x. So you're going to have a couple integration by parts. Ugh. Right? And then you're going to have another integration by parts to do when you take the y partial of this. And then, by the way, you're going to have to take the z partial of that thing. And a side note, it turns out you can't do the z partial of that function. It's not... it does not have an antiderivative with respect to z that you can write without series. Excuse me. So highly undesirable to take an anti-partial here, whatever that's worth. So the way it turns out that this problem is more tractable is to realize that, we'll get around to computing f in a minute, but what happens when I plug in, if I plug in t equals 0, and then if I subsequently plug in t equals 1, what are these two, starting points? What are the starting point and ending point? And it turns out in this case they're the same. A little bit of arithmetic. Plug in. By the way, I assume, and this is a reminder, but remember this class assumes that you're good with trig, and one of the many things about trig that I want you to know, we will assume that you know, is how to evaluate the trig function. So make sure to know sine of 0 and sine of pi and stuff like that. Okay. So this curve starts and ends at the same point, and so if you want to use the fundamental theorem of line integrals, you can say this integral is f of b minus f of a, which I'm going to rewrite as, b is equal to a, so this is f of a minus f of a. And now you realize, ugly though it would be to find f, I don't actually need to. Simply knowing that it exists is enough for me to conclude here, therefore, that difference is 0. So, that's kind of a nice little convenience. Yeah? Everybody good? Let me show you a different way that you can solve this problem. I think this is a nice one. Let's go back to the diagram for a second here. We computed that curl. We got 0. That means that my integrand here would be 0, and a lot of students will see daylight at this point. They think, I can just compute a double integral of 0. That was, of course, going to be 0. Therefore, the integral is 0, and I'm done. And turn the page and walk away. And this is the landmine. We've talked about this before, right? This is a very dangerous landmine to assume just because your curl is 0 that means that you have an integral in the first place to plug that 0 into. And that's not obvious. Right? So a very significant portion of the solution of this problem is to consider, is there an anti-boundary to my curve? Right? Does this integral here even exist? And side note, if the answer is no, if there is no anti-boundary, if the integral therefore does not even exist, and then all that business about the integrand is equal to 0, no, there is no integrand, because there is no integral, and it's all garbage. Right? So that's a dangerous little landmine. So on this problem, what you would have to do is you'd have to come over here and address the question, this curve, is this curve the boundary of something? And we've already made most of the answer to that. And notice that it starts and ends at the same point. Now, it's an ugly curve, so I don't know what kind of wacky nonsense it's doing along in there, but it does start and end at the same point. And so we can, for the purposes of Math 212, treat it as if, and this is usually true, and even when it's not, it's still actually a victimless crime. This always will work out. You can always pretend like there is a surface in here whose boundary is that curve. Okay. So you can make that observation, rewrite this then as a flux through the anti-boundary surface of curl. You've already confirmed that this is 0, and therefore that integral is 0. Everybody good? Okay. Remember, this class is about ideas, not answers. Right? And so, likewise, our tests are about reasoning, not numbers. Right? So, make sure that your thought process is evident. I have the advantage here that I can talk and use my mouth, right? So you'd want to annotate here a little bit more. Put in a couple of words along in here about how you know that there is a surface, because the curve starts and ends at the same point. Okay. All right. Okay, next one. So let's suppose we are computing another line integral again in R3. So again, we are here, and let's go. Therefore, again, we compute the curl. Let's see what we get. And yeah. So here our curl is, well, okay, look, one step at a time. 0 minus 1. 0 minus 1. And then 0 minus 1. Okay, so we get -1, -1, -1. So there's our curl. It's not 0. Did not get 0. Therefore, there is no anti-gradient. Therefore, the fundamental theorem of line integrals off the table. It's not a candidate. Don't write f of b minus f of a anywhere on the page. That doesn't make any sense. And curl tells us that. Okay, well, so that's not good news. Makes it look like then our only candidate, as far as one of these fancy boundary theorems goes, would be to use Stokes' curl theorem. So, okay, well, I guess I've got to look at my curve that I've been given, and I've got to ask, is that curve a boundary of some surface? Okay, so back to the question. What does our curve look like? We have a vertical cylinder intersecting a plane. Vertical cylinder intersecting a plane, and so we're going to get a tilted ellipse like that. All right, everybody see the picture there? So that's our curve. And again, the big question, is that the boundary of a surface? Why, yes it is. It is the boundary of that surface. So if I wanted to, and again, big if, this is just a candidate, but I could apply Stokes' curl theorem. There is my surface. Right? Notice that surface is part of this plane. You got to have a picture. The picture will tell you things like this. That surface that I'm choosing is clearly part of that plane, which has that equation. I can parameterize that plane without that much trouble. It's a graph. For one thing, I could solve for z in that equation, use the graph parameterization, and we could do this thing. Right? That's an option. It's on the table. Again, make sure to always consider all your options and think about what's likely going to be the most reasonable way to do the problem. And so look, if we want to turn this line integral into a surface integral, we can do that. Is that going to be a win, though? I mean, does that help us? The parameterization's actually kind of reasonable. The main problem, as I would see it, is if you look at the range of values of u and v, of course, being x and y, because we're using the graph parameterization, we have these bounds like that, right, that are going to involve either square roots or polar coordinates. Polar coordinates is reasonable. That's probably the way I'd do it. But if you do it in polar coordinates, then keep in mind every x that you see has trig in it. It's r cosine theta at this point. Right? And so, I mean, there's going to be trig in your question if you do it that way. Not that that's a deal breaker, but notice it's not sort of an immediate, just because Stokes' theorem applied does not mean that, oh, well, then everything's going to work out well. Right? So that's a big point to keep in mind about these vector calculus theorems. They're not magic wands. Right? They just allow you to turn a question into a different question, which also might stink. So keep that in mind. I'll tell you what I would do on this question. I think I would just take the original curve. Parameterizing the curve is actually pretty straightforward. On that curve, notice that as I go around this curve, x and y are just going around that loop. X and y are, how about cosine t, sine t? Right? That would be a really easy way to parameterize the x and the y coordinates. Now, what can I say about the z coordinate, though? Well, z is easy to solve for. It's just negative x minus y. So, now there's a little trig in that, too. But it's a one-dimensional integral, not a double integral. And there's kind of just a lot less steps involved. Just, I think the easiest way to solve this problem is brute force parameterization of the curve and do the pullback. You know, dx is x prime dt and all that. I think that's your easiest way to do the problem. So what do y'all think about my strategizing and consideration of the options? Does anybody have any questions about any of that? Are you happy? Okay. All right. Oh, excuse me. By the way, I apologize for the voice and the coughing and stuff. I've got a cold or something. Another question. Now, this one looks very, very similar. You'll notice it's the exact same vector field. We're still looking at that same vertical cylinder intersecting a plane. The only thing that's different is it's now a different plane. And the reason I have this example in here is just to point out that we'll look at sometimes things work out nicely. And other times they don't. But in this case, things are going to work out really nicely. So we have the same picture up here, pretty much. It's just that now, this plane, I'm not going to redraw it. It's, not like it was to scale in the first place anyway, right? So I've got a different equation for my plane. So my surface, if I were to draw the surface here, its normal vector is easy to write down, and I'm just going to say normal. I don't want to say lowercase n because these days that would suggest it's a unit normal vector, and I don't want to deal with that. And I also don't want to use capital N because I very importantly am not thinking of this, what I'm arguing here as being from the parameterization. I just want to be able to write down conveniently that my normal vector, a normal vector, is 1, 0, and negative 1. Okay. And recall that our curl is the same. Just negative 1, negative 1, negative 1. So in this question down here, if you were to compute this with Stokes' theorem, notice that you would end up doing a dot product. Here, let me go ahead and unitize this because I guess we can. Not that much trouble at this point. My normal vector is that divided by the square root of 2. At this point, using Stokes' theorem, color choices. My Stokes' theorem would have me crossing those two vectors. I'm sorry, dotting those two vectors. Right, so curl dot in ds, remember? Well, that dot product's 0. So, always a good thing to, again, just kind of head on a swivel, always be kind of looking for the possibility that something cool might work out, and in this case it does. So here I would, for this question number 4 down here, I would not suggest that you parameterize and pull back. Well, you could. It'd still work. It's fine. But here, Stokes' curl theorem would be sweet. Everybody happy with that? Everybody good? Alrighty. Okay, so here's another one. Let me ignore the hint for a moment. We'll come back to that in a few. Here we're computing a flux. Okay, now wait a second. This is our first flux example that we're looking at. So let's remind ourselves how that changes things. We're looking for a flux. So these are our candidate theorems. Right? The diagram tells me I should compute the divergence to see what I get. That'll either be my integrand, or it'll tell me whether the anti-curl I'm looking for even exists. So let's do that. Let's compute the divergence of this vector field. And, well, let's see. The x partial is z. The y partial of that is negative z. And the z partial of that, of course, is 0. And I get 0, which is good news. Tells me a couple of things. If the divergence is 0, right? Because I get 0 here, there is an anti-curl. I don't know how to find it, but there is one. And so Stokes' curl theorem is at least kind of on the table. Okay. It also tells me, and don't forget, you got to keep your options in mind, surface independence. Right now, we kind of sneered at path independence a couple examples back, because why would you use path independence? Just use the fundamental theorem of line integrals. It's so much easier, right? And that's very often true. But if you make the same sneer here, it doesn't hold, because using Stokes' curl theorem, not always easy. I mean, this exists, but I don't know how to find it, so it'd be a arguably hard way to solve this problem. And so all of a sudden, surface independence is looking like a good tool. Okay. All right, so let's go back over here and remind ourselves we do have to figure out what this thing looks like, so let's draw the picture. Okay, so we have that is a upside down elliptical paraboloid. Flashbacks to chapter 12. Hope everybody remembers all that chapter 12 business. Okay, so we've got an upside down elliptical paraboloid. We're looking for the part of that elliptical paraboloid where z is greater than or equal to 0. Right? So the part of the paraboloid that is above there. Now, I emphasize, I know I talked about this once before, let me say it again. It is extremely important to interpret questions, interpret from the phrasing of the question correctly. Right? A lot of students incorrectly, they look at the picture here and they think, okay, well then my surface must be kind of, all of that. And it's just not what this says, right? Intersection means that we're looking for points that are on the paraboloid, and furthermore, not alternatively, right? But in addition to having to be on the paraboloid, they also have to, be above the XY plane, right? So very importantly, this surface is just that. It's an upside down bowl. There's no saran wrap. Right? Is everybody on board? What I'm talking about? Okay, so this surface is not a boundary of anything. It's not a closed surface. So, going back to the diagram, our surface, big mess. Let me get rid of this. Our surface, simply not a boundary. There is no anti-boundary. Gauss's divergence theorem does not apply. There is no triple integral to even entertain an integrand of. Right? So, no Gauss's divergence theorem here. Yeah? Okay. Okay. All right. So Stokes' curl theorem works, but I don't know how to find the anti-curl, so I don't know what to do with that. Gauss' divergence theorem doesn't work. I don't like either of these options. And so the fact that we had surface independence, remember divergence was 0, therefore we have surface independence. That's really our best option. So going back to the picture, here's our surface. And can I think of a surface that has the exact same boundary as our upside down bowl? Our upside down bowl has as its boundary this curve. Oh, let's think about orientations. Here we go. My original surface is oriented up, so that means that my new surface here, clearly I'm going to pick that one, oriented in the direction that gives me the same boundary orientation, which is that way. Right, and you just got to sit there and use your thumb, fingers, right? Think about the swirls. And let's see here. So this orientation there tells me that orientation on the boundary, which gives me that orientation on my new surface. Or, strategically speaking, just, if only as kind of a little check to yourself, you can think of your original surface and kind of slowly deforming it. And as you slowly deform it, let the normal vector kind of slowly deform along with the surface, and that will get you to the right answer. As long as these two surfaces are deformable in this way. So we've got ourselves a new surface, and life is actually really good on this. Let me get rid of this old surface. We don't like that old surface anymore. On this nice, pretty, flat, green surface, it's real easy to write down the normal vector. Right, 0, 0, 1. And this integral is easy to work out. In fact, it's super easy to work out, so keep in mind we're looking at flux of F dot n, and when n is 0, 0, 1, and F is xz negative yz 0, then notice the dot product is immediately 0, and so life is really good. Let me put my ds there to be careful. There you go. 0. Everybody happy? All right, now I want to show you another way to do this problem. It uses this hint here. Now, were this hint not given, it'd be hard to see how this would work out for you. But sometimes we give you little hints because we want to encourage you in a certain direction on a question. The hint says my vector field is the curl of that other vector field, and so now you can check the algebra. It works, right? The curl of that thing is that thing. Right? How would you use this? Well, let's go back to our diagram and remember, Stokes' curl theorem is valid here. I mean, it's fine. The divergence was 0. There is an anti-gradient. I just didn't know how to find. I meant anti-curl. Excuse me. I just didn't know how to find the anti-curl. Right? So, if the anti-curl is in fact sort of kind of given to us, then I do know how to find it. I say, thank you. Right? If it's given to you, that's all you got to do. So that's in fact what this says. This says this vector field is the anti-curl because its curl is the original field. Right? So knowing that, this is your anti-curl. Stokes' curl theorem says that I can just take a line integral around the boundary curve of the anti-curl dot dx. Yeah, just Stokes' theorem. Okay, now how is this a win? Well, it turns out there's some nice things you can say about dx. Let me remind you what this surface looks like. Our surface, again, is this. So that means that the boundary is like that. That boundary is entirely in the xy plane. And that means, because it's entirely in the xy plane, that means that z is constant, and therefore dz is equal to 0. Right? So our dx vector is dx, dy, dz, but dz is 0. Right, and so again, this is the lucky break. It just happens to work out super nice. That I get 0, 0, 0. I'm taking an integral of 0 again. Everybody happy? Any questions? Okay. All right. So there's two good ways to solve this problem, even with the hint given. You see this hint. One reasonable approach to take is, you're telling me my vector field's a curl. Being a curl means surface independent. You don't even have to compute the divergence in that case, right? It's a curl, of course. The divergence is 0. And so surface independent. Throw away the old surface, give yourself a new surface, and do like we did before. Or, if you want to use Stokes' theorem, perfectly fine as well. Okay, last example, and let's see, we're short on time, but this is a quick one. Another flux. Let's identify where we are on our diagram. We are again looking for a flux. We again, therefore, have these two candidates. Let's, as the diagram suggests, compute the divergence, see what we get. The divergence here. Well, let's see here. The x partial is 1. The y partial is 1. The z partial is negative 1. So I have 1 plus 1 minus 1, which is 1, which is not 0. I don't get 0. There is no anti-curl. Stokes' curl theorem is not on the table. It doesn't matter what the boundary curve is. You just can't use Stokes' curl theorem. Okay. All right. But that said, our our divergence is, even though it's not 0, it's still kind of nice. It's just 1. Right? I can then ask the question, okay, well, what about my surface? Might my surface be the boundary of a three-dimensional solid? And, okay, well, let's go back over here and, oh, my God, look at that. Our surface is a sphere oriented outward. That is a boundary. This S here is the boundary of a ball, for example. This solid ball here. There you go. So you can rewrite this with Gauss's divergence theorem. Right? You can't use Stokes' theorem, but this is just a triple integral of divergence over my new solid. So I have triple integral over the ball. Triple integral of divergence. My divergence, of course, we already computed. My divergence is 1. And what I have then is just the volume of this three-dimensional ball, and that the standard, high school geometry, geometric solid. So 4/3 pi r cubed is the unit sphere. So r is 1. So just 4/3 pi. Yeah. Everybody on board? Okay. Wow, we did that in 2.5 minutes. Okay, so the very last thing I guess I'll say, just, spend some time over Thanksgiving. By the way, have a good time. I hope everybody enjoys themselves and relaxes. I don't want you to spend 8 hours a day doing math. I think that would be wrong, right? But I also don't think it would be a good idea to do 0 math over break, right? Remind you, spend a little bit of time thinking things through. Just try to make sure that you don't come back from Thanksgiving less well prepared than you are now, I think that's a good bare minimum, right? And of course, it's also a good opportunity to catch up. Look at all the use that we've made today of these diagrams. I hope y'all will take this really seriously and, try to make as much use as you can of the diagrams. And by the way, memorize the diagrams. I know that sounds outrageous, but it's not. The patterns are so strong, you might inadvertently have already memorized this diagram. Right? So, I think it's a very good exercise. If you haven't memorized the diagram, take out a clean sheet of paper, see how much of it you can get. You might just surprise yourself. And then whatever parts you don't get, that's a good little tip in your mind of, well, okay, why didn't I remember that? Why couldn't I see how the pattern extends there? That might be a good thing to spend a little bit of time on. Have a good break. See y'all later.